Hello friends, this video on Thermodynamics part 21 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure that you have watched part 1 to part 20. So, Hess Law of constant summation, the next topic, and this actually the last topic which we have shown, the Born-Haber cycle, is actually based on this Hess Law itself. And this is derived basically because of the fact that the enthalpy is the state function. So you know the enthalpy is the state function. So enthalpy change is same whether you do it in one step or series of steps, as we have seen in the last Born-Haber cycle, right? So the Hess law says that if the reaction takes place in several states, then standard enthalpy of the reaction is sum of the standard enthalpy of the intermediate reaction. For example, if you want to find the standard enthalpy of reaction, it takes in different steps. You just add all the steps. This is what you get here. For example, let's suppose I have to burn the carbon. I have carbon, I burn with oxygen, I get, let's suppose, carbon monoxide. I got delta H as minus 110.5 kilojoule. I got this carbon monoxide, I again burn with oxygen, I get CO2. Here I got delta H is to be minus 283.0. If you add these, this gets cancelled. You get carbon plus O2 is CO2. So delta H actually will be sum of these, that is minus 393. So delta H of this is left up with 1 and 2, because I have to find the enthalpy of burning or combustion of carbon. So I did this thing in 2 steps, step 1, step 2. In step 1 I burned the carbon, get carbon monoxide. In second step I burn the carbon monoxide to get carbon dioxide. You add these steps and you get this. It's just a very simple law that if you want to carry out a reaction in multiple steps, you can do it, and you will get the same enthalpy. You just add all the enthalpy of all the steps. There are various applications of Hess law. It has helped to find the heat of formation. It has helped in determining the enthalpy of transitions, enthalpy of hydrations. It has also helped to determine the standard heat of reaction, and also ionic salts. And we have seen for lattice also, lattice enthalpy, it is used to find using Haber's law. Haber law also, you see, is based on this Hess law only, Born-Haber cycle. So these are used because it's just like a mathematical puzzle. You have this big value and it is there are so many other small values. You know all except one, you can find that. Just a mathematical equation. Hope you understand. See, because it says that the enthalpy of a big reaction is nothing but if you break this reaction into multiple small parts, you add them, you get it. Sometimes it's very difficult to find the enthalpy of heat of formation, transition, hydration. It's difficult. So what we can do is we don't find that part, but other things we find, and then mathematically we find this part. For example, we saw in the last Born-Haber cycle, it was the lattice enthalpy, which was difficult to find. But other things were easy to find. NaCl we found using some other process, we got some value. And this also, we did some other process steps, we had the value for that. And we have put all the values and we got the lattice enthalpy of sodium chloride. We'll take some examples that will make things more clear. We'll find the enthalpy of combustion of glucose from this following data. So the reaction I am looking for is the combustion of glucose. That is, you have C6H12O6. You add oxygen to it, it becomes CO2 plus water. Balance this 6 carbon with 6, hydrogen 12 with 6, and then 6. So to form this reaction, what I can do is, if I can flip this reaction, this is the reaction 1, 2 and 3. Let me flip this reaction and see what comes. C6H12O6 gives 3O2 plus 6H2 plus 6C. The delta H will be, you flip it, it's become positive, 1169.8. This is what I got. Now I need 6O2. Right? So what I can do is, and also I have hydrogen here which I want to delete because I don't have this hydrogen here. So I have to get rid of these 6 hydrogen. So I can have a reaction where 6 hydrogen comes here, right? So I have this second reaction multiply with 6. So what I'll get is 6 hydrogen plus 3 oxygen gives 6, and delta H will come out to be, multiply this with 6. What you get is, that is 16165. So I have hydrogen also gone. I have 6 carbon here which I want to remove. So I have to have a reaction where I have 6 carbon here. I can multiply this with 6. So I get 6 carbon plus 6 O2 gives 6 O2. And delta H will be minus 237. So if you add this reaction, if you see 6C gone, 6H2 gone, we have 3O2 here, 3A2 gone. If you add this reaction, what I get is glucose plus oxygen gives 6 carbon dioxide and water. Exactly same reaction. So delta H for this reaction will be, you add all these values. So what you get is this is all minus, I think, yeah. This minus this minus this. Correct? So delta H for this reaction will be 1169.8 minus this guy 1616.4 minus 2370. So it's all this, it comes out to be minus 281.6, and that is my answer. Easy one. So with Hess law, without even doing this reaction, without even performing this reaction, I was able to find the enthalpy change that will take place if you burn the glucose, or I was able to find the enthalpy of combustion of glucose. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.